Welcome to Intro to Functional Programming in Haskell. Today we're going to be talking about monoids and functors. So before we dive into what monoids and functors specifically are, let's talk about algebras. For composability's sake, we often try to work with the most general principles and rules we can in Haskell. Within programming, we're working with data and operations on that data. This leads us to the concept of algebras. An algebra is a set of operations and a set of values and a set of guarantees about how those operations behave when used on values in the appropriate set. These guarantees are also known as laws. So an algebra is composed of operations, values, and laws. Functor and monoid are both algebras. So any binary associative operation with an identity forms a monoid over the valid values it can operate on. So, like we just discussed, monoid is a kind of algebra. An uneasy to understand example of a monoid is addition in conjunction to integers. So the addition operation forms a monoid over integers. The addition operator takes two arguments, so it's binary. Grouping or parenthesization of additive expressions has no effect on the returned value, so addition is associative. And when addition is carried out with one of the arguments being 0, the other argument to the expression is always returned unchanged. So addition has a concept of identity. So monoids all must follow the laws of associativity and identity. Following identity means that there's some value that when we put it into the binary associative operation, it simply returns the other argument to the binary associative operation. In other words, the monoid's function must have a certain value that when we plug that value in, the function becomes equivalent to the identity function. So if you recall, ID x always returns x. Identity only ever returns what is given to it. The value that causes the binary associative operator to behave in this way is often referred to as mempty. The associative operation itself is generally referred to as mempty. So in particular, if we have a binary associative operation and a valid mempty value for that operation, we have a monoid. To know if our monoid is truly a valid monoid, it must follow these laws for all valid values of x, y, and z that are within the monoid's defined set of values. Multiply mempty x equals x, meaning when we, as we said before, use mempty in the binary associative operation, it becomes equivalent to ID. The second rule here simply re-expresses that notion, and also expresses the concept of associativity. So multiply with an x value and mempty should result in that same x value. And in general, multiply that uses mempty is a function that still takes one more argument, and that function is then equivalent to the ID function, which still also takes an argument. The second to last rule here further expresses the concept of associativity. All monoids must be fully associative, and thus mappend x, mappend yz should be equal to mappend xy, y to z. And this last rule is actually more of a guarantee. So mconcat is a function that you're guaranteed to have when you have a valid monoid. Mconcat is equal to fold r mappend mempty x. So looking back to the folding operation that we described in the other video, mconcat is essentially fold building a monoid instance using the mempty value as the accumulator, meaning mconcat is a summarization of how to fold with a given monoid. You can the final important concept being that all valid monoids can be intelligently folded and result in a meaningful value. Functor is another kind of algebra. A functor consists of a container type f and a function fmap that takes functions as an argument and lifts them. So what does lifting consist of? It consists of taking a function that takes a's and returns b's and turns it into a more widely applicable function that can take an f of a and return an f of b's. For example, if we had a list of integers and we had a single function that would take an integer as an argument and return 2 times that integer, fmap would take that function and return a new function that could take a list of integers in this case and return a list of different integers in this case. Taking note that a and b can be any type. So a and b can be, if you want, 2 different types. It's just that we could also have a function that took integers and returned characters. So in sum, all valid functors follow these laws. The first is that of identity, meaning fmap of id produces a function that is identical in effect to just using the id function on valid contained values. Imagine for a moment you have a list of integers and a function that takes an integer and returns a character, and another function that takes a character and returns a totally different integer than the one that we began with. The fmap of this first f function composed with the second function g is the same as f mapping f over our initial list of integers and then applying the f map of g over our initial list of integers. More concretely, the f map of f composed with g should be equivalent to the f map of f composed with f map of g. More generally, these first 2 laws are actually just trying to express this third law of structure preservation, meaning fmap should have a type that matches the type it is defined to have, meaning fmap involves a functor f and takes a function that goes from a to b, and can be, that function is then lifted, and this new lifted function can be applied to an f of a's and return an f of b.